Scientists discover CO₂ and CO, that's carbon dioxide and carbon monoxide, in ices in the outskirts of our solar system, according to University of Central Florida. For the first time, carbon dioxide, carbon monoxide ices have been observed in the far reaches of our solar system on trans-Neptunian objects, TNOs. A research team led by planetary scientist Mario Nascimento de Pará and Naomi Pinala Alonso from the University of Central Florida Space Institute, FSI, made the findings by using the infrared spectral capabilities of the James Webb Space Telescope to analyze the chemical composition of 59 trans-Neptunian objects and centaurs. The pioneering study published this week in Nature Astronomy suggests that carbon dioxide ice was abundant in the cold outer regions of the protoplanetary disk, the vast rotating disk of gas and dust from which the solar system formed. Further investigation is needed to understand the carbon monoxide ice's origins, as it's also prevalent on the TNOs in the study. The researchers reported the detection of carbon dioxide in 56 TNOs and carbon monoxide in 28, plus 6 with dubious or marginal detections, out of a sample of 59 objects observed with the James Webb Telescope. Carbon dioxide was widespread on the surfaces of trans-Neptunian population, independent of the dynamical class and body size, while carbon monoxide was detected only in the objects with a high carbon dioxide abundance, according to the study. The work is part of the UCF-led Discovering the Surface Compositions of Trans-Neptunian Objects program. One of the James Webb program focuses on analyzing our solar system. It's the first time we observed this region of the spectrum for a large collection of TNOs, so in a sense everything we saw was exciting and unique, says Depras, who co-authored the study, saying we did not expect to find that carbon dioxide was so ubiquitous in the TNO region, and even less that carbon monoxide was present in so many TNOs. The discovery of the ices can further help us understand the formation of our solar system and how celestial objects may have migrated, he says. Trans-Neptunian objects are relics from the process of planetary formation. These findings can impose important constraints about where these objects were formed, how they reached the region they inhabit nowadays, and how their surfaces evolved since their formation. Because they formed at greater distances to the Sun and are smaller than the planets, they contain the pristine information about the original composition of the protoplanetary disk. Chronicling ancient ice, carbon monoxide ice was observed on Pluto by the New Horizons probe, but not until James Webb was there, an observatory powerful enough to pinpoint and detect traces of carbon monoxide ice or carbon dioxide ice on the largest population of TNOs. Carbon dioxide is commonly found in many objects in our solar system, so the DISCO team was curious to see if it existed in greater quantities beyond the reaches of Neptune. Possible reasons for the lack of previous detections of carbon dioxide ice on TNOs include a lower abundance, non-volatile carbon dioxide becoming buried under layers of other less volatile ices and refractory materials over time, conversion into other molecules through irradiation, and simple observational limitations, according to the study. The discovery of carbon dioxide and carbon monoxide in the TNOs provides some context while also raising many questions. While the carbon dioxide was probably accreted from the protoplanetary disk, the origin of the carbon monoxide is more uncertain, he says. The latter is a volatile ice even in the cold surfaces of the TNOs. We can't rule out the carbon monoxide was primordially accreted and somehow was retained until the present day. However, the data suggests that it could be produced by the irradiation from carbon-bearing ices. An avalanche of answers. Confirming the presence of carbon dioxide and carbon monoxide on TNOs opens many opportunities to further study and quantify how or why it's present, says Pinilla Alonso, who also co-authored the study. The discovery of carbon dioxide on trans-Neptunian objects was thrilling, but even more fascinating were its characteristics, she says. The spectral imprint of carbon dioxide reveals two distinct surface compositions within our sample. In some TNOs, carbon dioxide is mixed with other materials like methanol, water, ice, and silicates. However, in another group, where carbon dioxide and carbon monoxide are major surface components, the spectral signature was strikingly unique. This dark carbon dioxide imprint is unlike any observed on other solar system bodies or even replicated in laboratory settings. It now seems clear that when carbon dioxide is abundant, it appears isolated from other materials, but this alone does not explain the band shape. The scientists understanding these carbon dioxide, they said, bands is another mystery, likely tied to their unique optical properties and how they reflect or absorb specific colors of light, she says. It was commonly theorized that perhaps carbon dioxide may be present in TNOs, as carbon dioxide exists in a gaseous state in comets, which are comparable in composition. In comets, we observe carbon dioxide as a gas released from the sublimation of ices on or just below the surface, she says. However, since carbon dioxide had never been observed on the surface of TNOs, the common belief was that it was trapped beneath the surface. Our latest findings append this notion. We now know that carbon dioxide is not only present in the surface of TNOs, but is also more common than water, ice, which we previously thought was the most abundant surface material. This revelation dramatically changes our understanding of the composition of TNOs and suggests that the processes affecting their surfaces are more complex than we realized. Thawing the data. Study co-authors Elsa Henault, the doctoral student at University Paris and the French National Center of Science Research, brought a laboratory and chemical perspective into interpretation of James West Telescope observations. Henault analyzed and compared the absorption bands of carbon dioxide and carbon monoxide across all objects. While there was ample evidence of the ice, there was a great diversity in abundance and distribution, Henault says. While we found CO₂ to be ubiquitous across TNOs, it's definitely not uniformly distributed. Some objects are poor in carbon dioxide, while others are very rich in carbon dioxide and show carbon monoxide. Some objects display pure carbon dioxide, while others have it mixed with other compounds, linking characteristics of carbon dioxide to orbital and physical parameters. The researchers brought some definite answers to long-standing questions dating back to the discovery of TNOs nearly 30 years ago, but researchers still have a long way to go, Henault said. And this is provided by the Central Florida University, by Eddie Duriz, the University of Central Florida, on phys.org. Please leave your comments, and thank you for your support. Please support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support, and that you find all my content so interesting. You'll find the Patreon account details in the description box below.